In this last video, for section 4.1 on exponential growth and decay, we're going to learn about changing units in our exponential functions. So sometimes in our exponential functions, it's useful to change from something like days to weeks, or maybe weeks back to days. You could go from years to decades, so on and so forth. Here's an example. If we have a daily decay factor of 0.89, then we would need to multiply by 0.89 7 times to get the decay for a whole week. So what that means is our daily decay factor becomes a weekly decay factor by multiplying by 0.89 7 times. So we take 0.89 and we put 7 in the exponent. This is something that you'll probably want to put in your calculator, and when you do, you'll get 0.44, and I've rounded this to 2 decimal places. Let's go back to our first example where we were talking about the exponential growth of a disease. And remember, that disease doubles every week. But what I want to do is change this weekly growth factor into a daily growth factor. So here's what we're starting with, a weekly growth factor of 2. So if we were looking at our function, if we wanted the growth for W weeks, we would put W in the exponent. And remember that a day is 1/7 of a week. So for one day, we would put 1/7 in the exponent. That's how we get the daily decay factor of 2 to the 1/7 power. This idea can also come in handy in examples like this, where we have a radioactive isotope of carbon-14 with a half-life of 5,770 years. But what I'm interested in is not the half-life. I want to figure out the yearly decay factor for carbon-14. Let's think through how this works. After H half-lives, so this could be 1, 2, 3, or maybe half of a half-life, carbon-14 will decay by a factor of 1/2 to the H power. So for 2 half-lives, you would put 2 in the exponent. For half of a half-life, you would put 0.5, or 1/2 in the exponent. Since our half-life is 5,770 years, 1 year is 1 out of 5,770 half-lives. So that means to get the yearly decay factor, we have to put this amount, 1 out of 5,770, in the exponent of 1/2. So that's what I've done down here. And then I put this number in the calculator, and we get this. So it's very close to 1.99988, but not quite. So that means after each year, there's just a little bit less carbon-14 left over. And I've rounded this to 5 decimal places. Now that we have the yearly decay rate of carbon-14, we can make a formula for the amount of carbon-14 that remains after T years. In this particular example, I'm going to start with 32 grams of carbon-14. So think back to the way that a formula for an exponential function looks like. The amount remaining will be equal to the initial amount times the decay rate, or the base, to the t power. And all we have to do is plug in our numbers. And I've just discovered another little mistake here. This should be 32. So we plug in our initial amount of 32 grams, and then we plug in the decay rate that we just found, the 0.99988, and then we bring down our exponent t. So using this new formula, we could figure out the amount of carbon-14 that remains after any number of years just by plugging in that number here in the exponent.